We have Derek speaking to us. Derek was an REP at TTIC until 2 weeks ago. So this is Derek's farewell talk from us, but not. We'll probably still see him. I hope we'll still see him a lot. So Derek is across the midway and started a position in now I'm gonna have to cheat. The Institute for Population and Precision Health in Chicago, and will tell us about some work he's done here during his time here at TTIC, and that I'm hoping I assume he's going to continue doing across the Midwest. So thanks, Derek, for both your time at TTIC and here. Oh, I need to open this, and then you need to also unmute. Okay, sorry.
It's already unmuted.
So this is Derek's slides, and this is. Okay, now unmuted. There is a sensitive mic recording here. Okay.
Alright, so thank you for the introduction. Like Natty said, I was here until April 1st, and I didn't move too far. I moved to the Institute of Population and Precision Health, which is on Chicago. So basically, we're at TTIC right now, and the Institute of Population and Precision Health, or IPPH, it's a little distributed, but our main offices are in Mitchell Hospital, if you've ever been there. It's about a 20-minute walk, so like on a day like today, it's quite nice. And it's an institute that really focuses on interdisciplinary research, bringing in kind of clinicians, biologists across the academic institutes of Chicago and the Chicagoland area. And before I want to kind of structure this talk, in the beginning, I want to talk a little bit about the institute, maybe garner some interest in AI and health. And then in the second half, I kind of want to talk about AI's role in health over the years. I'll go into a little bit of a work I did here, which was in collaboration with IPPH, to kind of show how it is framed, and then end with what maybe the future looks like in AI and healthcare. So in order to kind of talk about the Institute of Population and Precision Health, we need to kind of talk about two words, that's population and precision. And so these are two different perspectives on looking at health. So population health focuses on health outcomes of a group, and so the way we kind of look at this direction of research is not so much as treating the individual, but looking at underrepresented populations at risk, and there's three key components of the health outcomes. So that could be things like mortality, disease prevalence. And then we have health determinants. So these determinants, such as accessibility to healthcare, behavior, your social environment, these generally shape what we kind of describe or observe as disparities. So these could be population disparities based on race, ethnicity, gender, geography, and we see kind of a change of distribution of these health outcomes within these disparities. And the goal of this research is to identify and design these policies and programs to correct these disparities kind of at the root. And what population health has discovered over past decade or two is that there's four distinct characteristics of factors we can look at. So with healthcare, or access to healthcare, the quality of healthcare of a specific population, health behaviors, that could be smoking, exercise, diet, your physical environment, and then social determinants, that could be your education, your job status, your family support, your income. And something that's been quite interesting is that research has shown that these social and environmental factors, your education, where you live, are often one of the more significant, or kind of even the most significant impact on kind of health, depending on kind of disease or risk you're looking at. And so this has shift kind of, and we'll talk about kind of these paradigm shifts in health. So in the case of population health, there's paradigm shift of treating kind of from a reactionary standpoint of an illness to preventing disease of a population by addressing some root cause. And so kind of an example of social determinants of health, you can think about economic stability, physical environment, so your housing, your transportation, the walkability, the green spaces, your education status, food, so your food security, access to healthy food, community and safety, so that causes a lot of stress if you're in a more violent or traumatic area, as well as access to healthcare. So if you can't get good quality of health care, then your health generally deteriorates. So an example kind of in the Chicago area was a research that was done back in 2022 looking at obesity prevalence in Chicago to kind of give an overview of what population kind of health looks like. Is if in the top left we look at the distribution of obesity prevalence, you can see the darker areas more prevalent, and we can kind of look at how it relates to different aspects of those populations. So green spaces, how many parks, biking ratio, the walkability, the bikeability of things, unemployment rate, poverty, crime ratio, and so forth. And I think what they found in this study was that walkability and severe rent and income were generally associated with obesity prevalence. So this kind of frames the whole shift of population health research. Rather, we're moving from treating individuals only when they're sick, so this reactionary approach, to managing health outcomes of groups. This episodic care framework, where you just see a patient once and they leave, and then you only see them when they come back, to this continuous monitoring. And then a clinically only focus of research to more broader and social determinants of health. On the other hand, we have precision health. And so this kind of moves in the other direction. So precision health, rather than focusing on the group, focuses on the individual. And we want to generally look at data more specific to individual characteristics. That could be genetics, your DNA, your specific environment and lifestyle, your individual biology. And the goal is to move away from a one-size-fits-all treatment plan based on population averages to more personalized approaches. And this may be more of the when you think of AI in healthcare, what you're more familiar with. So with precision health, we look at things like genomics, so we can think of how your DNA is mutated, what sort of alleles you have. Imaging, so we can take imagings of biopsies, X-rays, radiology, clinical labs, health records. We can take into consideration your lifestyle, the environment. And one of the kind of new and upcoming things is this continuous monitoring through sensors. So we've got smart devices. There's a whole field in biotechnology designed, or that's pushing research towards deployable sensors to collect continuous data that are not annoying to wear. So what this gives us is feature-rich data sets, but there's often challenges with missingness and noise. And the overall goal, as opposed to population health, is now we're looking at treatment recommendations for the individual, risk predictions at the individual level. And so we're moving from this, looking at a population average to make some sort of recommendation, to making individual level inferences. And so again, we can think of the shift from treating individuals based on these averages to tailoring individual treatments, this episodic care of coming and going, to continuous prevention and monitoring, and a clinical-only focus to integrating big data for treatment prevention. And so when you put them side by side, they look quite different. Population health looks at communities, demographics. Precision health looks at individuals. Population health tries to make better standard health interventions through policy changes. Precision health looks to make personalized and adaptive interventions for a specific individual. You can think of population health as like a macro level view of health research, and precision health as a micro level. And what the Institute of Population Precision Health focuses on is both of these, framing research in both of these, so emphasizing that healthcare can be both personalized but also equitable. And so kind of going back to the Institute, this is just kind of taken from their website, is the word precision in the context of population health simply describes the ability to prevent disease and promote health at the individual level by also considering the disparities in health populations. Can you remind me how long these talks?
You should. You started a bit late.
Yeah.
It'll be good to wrap up by noon.
Okay.
But we started a bit late, so we can maybe move it.
Okay. I'm just trying to get to more meat of it. So again, from their website, the IPPH, the vision and mission is really looking at precision health using that population-based framework. So scoping, their research direction, keeping that population-based health approach in mind. And the specific aim I want to focus on is really that first one, bringing together diverse expertise across, university and the Chicagoland area. Really do research relevant to precision health research and training. So IPPH is embedded in UChicago, but collaborates with people in the hospital, biological science division, the medical school. I think there's collaborations with Argonne and other institutes. So ideally, one of the goals of the talk is kind of also to maybe build bridges with research and students at TTIC. So to empower research at IPPH, they do a lot of initiatives, and the one that is, in my opinion, the most interesting and for my research probably going to be most impactful is the All of Us initiative through the NIH and under Illinois Precision Medicine Consortium. So this is an initiative led by the NIH where the goal is to collect a massive amount of data for precision health research, health records, genomic sequencing, surveys, physical measurements, wearable sensors, but also focusing on diversity. So, establishing these initiatives in underrepresented populations. So UChicago is kind of at the forefront of this. We serve a very underrepresented population in the south side of Chicago. And so I think, the goal of the All of Us is to collect over 1 million participants. And I think UChicago's collected over 100,000, if I'm not mistaken. But the access to the data is, kind of across all sorts of institutions. And so this is actually presenting a continuously evolving data set and a platform where we can, push clinical care research and other machine learning ideas. They have some other initiatives. I won't get too much into. A lot of them are, kind of more national or global, looking at, the environmental effect on population health, longitudinal studies to things like arsenic exposure, and then there's a couple of, Chicago-specific ones. The Chicago Center for HIV Elimination, Southside Health and Vitality Studies. So there's a lot of kind of data and cohort structures going on. I tried to summarize all of the research kind of going on in IPH in a couple different categories. So this by no means is all-encompassing, but I try to describe it the best I can. So there are 6 main kind of categories I pulled out. And so a lot of it is environmental exposure. So a lot of the research looks at, how things like air pollution, toxic exposures affect population health, and looking at how that changes the risks, and then how to create policies to prevent those risks. One of the more kind of significant diseases studied is cancer epidemiology, so population level risk factors for cancer, looking at access to screening and prevention strategies, and also strategies for earlier identification. And that kind of goes hand in hand with cancer disparities and health equity. And then more of, in mind, what I do is genetics, genomics, and molecular epidemiology, so uncovering kind of the molecular differences in patients and populations that are stratify risk and disease, immunology and immune-mediated mechanisms. So a lot of that work is done by Dr. Ali Khan, who is here at TTIC, and I've worked closely with over the years. Where we look at how the immune system can be very personalized and leveraging the immune system for therapeutic treatment. And the last is cohort data systems and computational methods, so how we can create diverse population data sets so that we don't introduce bias into these methods. Recently, the Institute has really advocated advancing AI-driven methods, which is one of the reasons why I joined. And these methods, they want to focus on diverse biomedical, clinical, and population level data in order to enable both precision level care as well as scalable improvements. So here's the core faculty from their website. Other core faculty, including myself, is Guihong Wan, who just joined as well. A lot of her research focuses in biomedical imaging. And so with that, I want to move into I've introduced the Institute. So now I want to talk about AI's role in modern medicine and kind of its past, where we are now, and where we might look to in the future. So I want to start with just telling a story. And a little disclosure, I made these images with AI, so if there's little hallucinations or little artifacts that don't make sense, just ignore them. I just need to get better at prompting. But we have 2 patients. They arrive at different hospitals with the same presentation, a subtle fever, elevated heart rate, early signs of infection, but nothing really definitive. Nothing triggers urgency on its own, and clinically both just look like a wait and watch type of scenario. But under the surface, there's structure to this data, not in any single measurement, but in the trajectory. Subtle correlations across vital labs, timing patterns, these all begin to resemble thousands of prior cases of deterioration. So individually, all this data is just noise, but together, it contributes to a signal. And so in one hospital on the left, medicine follows a traditional reactionary-based approach, threshold-based logic. You wait until clinical criteria are met, you react, you administer treatment. In the other, a model continuously updates a latent risk estimate. It integrates every new data point into a learned representation of disease progression. It's not classification, it's not rule-based, but rather it's continuous inference over time. And so at some point, the AI system crosses some threshold, not because a rule is triggered, but rather because the posterior probability of deterioration was just too high to ignore. An alert fires, and treatment begins 6 hours earlier. And so what we know is that in time-sensitive cases like sepsis, which is one of the leading causes of hospital mortality, hours matter. And so this 6-hour difference can lead to very different outcomes. And so the point of the story is, I want to reframe healthcare as not, AI helping doctors, not really even just, AI assisting, and definitely not AI replacing doctors. But rather it's a shift in this computational paradigm of medicine as a whole. We're moving, from these episodic decision-making practices to continuous prediction and inference, relying on summary statistics to using learned representations, leveraging population averages to, relying on individualized trajectories, and moving from static protocols to adaptive data-driven policies. And so, we've stopped kind of thinking of healthcare as, just a domain application of machine learning, but rather now a large, complex, real-world machine learning system where clinicians kind of work within. And this is faced with feedback loops, distribution shifts, partial observability, and life-critical stakes, meaning a single false negative could be someone's life. So the question is no longer whether AI belongs in healthcare. It's rather, how much of healthcare has already become an AI system, and how far will it go? And so we can talk about some early successes in AI in healthcare. So the first one, reinforcement learning for sepsis treatment, was one of the first kind of breakthroughs in AI in healthcare. We just kind of had a little story about sepsis. The reason sepsis was so important is because, like I said, it was the leading cause of mortality in hospitals. It was very silent. It was very hard to detect. And by the time, it was able to be detected, often it was too late. And this led to kind of a more broad application of early warning systems of deterioration, not just sepsis, but any form of, deterioration within a hospital setting. Having these models just continuously kind of observe patients, giving kind of this AI vigilance over populations, and catching those risks before it's too late. Another breakthrough, this is probably the most well-known breakthrough, is kind of convolutional neural networks for medical image. So you applying them to X-ray, other radiologies, interpretation, kind of facilitating diagnostics and leaving the burden on clinicians, making it easier to get through data. Predicting patient risk. This has kind of become a large part of precision medicine, where we can stratify patients across populations, predict risk, and enable proactive targeted interventions rather than that reactive care that's been traditionally used. And then lastly, genomic variant interpretation. So this is kind of when we now look at different mutations across patients and look at how these, not just how the mutations affect disease, but what impact they have on things like protein folding. We've had now these models like AlphaFold that have made breakthroughs in protein folding, where we can now kind of investigate how mutations affect the folding, which affect the function. At the same time, we've had a growth of multimodal data. So we've had this explosion of multimodal data, electronic health records. So these are structured and unstructured, data types. They could be clinical notes. They could be specific codes. We've got imaging data, radiology. We've got histopathology. We've got genomics. We can sequence data real cheap now at scale. We've got wearables and sensors. Everyone's got a smartphone, hopefully. We've got, people have smartwatches. There's a large biomedical field that goes into just developing, implants or wearable sensors that are convenient. And then we've talked about kind of in the population scope, we've got like this, also consider these environment and social determinants of health. And so from a machine learning and AI standpoint, I like to structure or frame this as, an aligned but very noisy multi-view representation learning problem. In addition to this growth of data, we've had kind of these births of large language models and the rise of foundation models in health. So all this different multimodal data, we now can learn these generalized foundation models to focus on core biological problems. AlphaFold won the Nobel Prize for its work in protein folding, which was, partially I think inspired by Jimbo here. And a key strength of these models lies in their capacity to learn accurate representations of these intricate biological data sets by leveraging kind of the large knowledge base that we've established over the decades. For example, protein language models can learn coevolutionary structures without being explicitly told, and that kind of gives rise to an inference of contact maps that you can kind of learn how they're folding. And there's a great flexibility in these foundation models. And so with this, I kind of want to talk about some of the work I did here now, leveraging foundation models in a population and precision health framework. And so the domain is medical image pathology. So when you have cancer, a lot of times what will happen is you will take a sample of that tumor, biopsy a skin tissue, you will stain it with specific coloring dye that'll kind of highlight different areas easier. You can take an image, and then a pathologist will look at it under a microscope and then make some sort of clinical decision. Is there cancer here? What kind of cancer? What stage of cancer? But what happens when you have a resource-constrained environment? So, for example, this data set comes from Bangladesh, where oftentimes the closest hospitals, 200 miles away, they may not even have an expert pathologist. And so, how can we make diagnostic healthcare equitable in these resource-constrained populations? And so we kind of had this idea to see, our foundation models that are now trained, on these large knowledge sets of just tissue samples. Can we apply those as, potentially in the future deployable service to assist, either experts, whether, these hospitals have to send samples off to experts and there's a bottleneck in, data processing, or, non-experts to kind of at least help make diagnostic decisions quicker before an expert can look at it. And we assist in that pipeline. And so the task is whole slide classification. So we have this tissue sample, and we want to, analyze it in some way. Well, in order to look at cells, it's a very high resolution. And so this is a massive image at high resolution. And so in order to kind of put it into a model, we cut it up into what are called tiles. So you chop this into very small pieces. And foundation models will generally use this tile encoder visual transformer. I think these were all Dino V2 driven foundation models. And these tile encoders will generate an embedding for each tile. Then in order to kind of go back to the whole slide, we need to take each of these tile embeddings and either construct a slide level embedding or do some sort of multi-instance learning. And you can use some things like attention to identify regions of interest, and we'll talk about why that can be useful for annotation later. And the ultimate goal of, can these models potentially be used to help resource-constrained populations? And so we compared 3 foundation models, UNI, Prof, GigaPath, and PRISM. So UNI was probably the first of its kind. It learns generalizable tissue representations using a Dino V2 framework with really no internal aggregation method. So it relies on things like multi-instance learning, where you just assign attention weight to each tile embedding to learn which are the most important tiles. We use Prof GigaPath, which is a gigapixel scale pathology framework, They do have an internal slide aggregation using a dilated aggregation. It's kind of their own work called LongNet. And then lastly, we use Prism. And I want to highlight in Prism that Prism had a little bit of a different task as a foundation model. Not only did it just learn to encode and decode the image frame or the image tiles, but also create a descriptive text of the whole slide, something like what a pathologist would write. And that means, not only, identifying the cancer, but how many pieces of tissue are on the slide, any morphological abnormalities other than cancer. And that's going to become important when we look at kind of what the models are doing. And so we took some data. This is generated from UChicago in Bangladesh. So this was a Bangladesh vitamin E and selenium trial, looking at not just a resource constrained population, but population at risk due to things like arsenic exposure. And so we've got about 2,000 H&E stained whole slides. So H&E is the specific dye to kind of turn it, that red-purple color. We've got 553 biopsies. And so we've got 4 different subtypes. We've got benign tissue, meaning there's no cancer. We've got Bowen's disease, which is a specific subtype of non-melanoma skin cancer. And to kind of note that non-melanoma skin cancer is also quite rare form of skin cancer associated with arsenic exposure. Basal cell carcinoma and invasive squamous cell carcinoma. So we can kind of see what each of these looks like. The basal cell carcinoma, slow growing, locally invasive. Lesions often arise in the epidermis, so that top layer of skin. Bowen's is squamous cell carcinoma, so lesions that have a prominent, what's this word? Skeratosis. So this is, you can see this kind of at all levels of the epidermis, so this will generally oftentimes transition into the third category of squamous cell carcinoma. And so this is much more invasive. So we see this, deep into the dermis, and it's much more aggressive. And so we can take all these tiles and have a kind of a standardized framework where we can evaluate, the foundation model itself as a performance. How well are these encodings it's learning? How well are the tile aggregation methods, either internal or something we can construct on our own? And we can also kind of use some classification downstream for cancer subtype prediction using these whole slide embeddings. And so without going into all the kind of benchmarking results, I think one of the most interesting things that came out of this paper was that when we had used Prism, one of the stark contrasts compared to the other two was that there was a much lower false positive rate of Bowen's, where it correctly either classified them as benign or squamous cell carcinoma. And the reason we believe that is because of the additional task of text annotation. And so when we look at the attention of the foundation models, as they made their whole slide embedding, one of the things is when you look at Pravika Path and Uni on the right, they're very similar. They look at just this cancer space, very limited. But when you look at Prism, it's scanning the borders of the borders of the tissue. It's kind of it's taking a much broader view as well. And we believe that's because it's from that multitask framework where not only is it trying to in our purpose identify this cancer subtype, but it's been trained to also step back and characterize everything as a whole. And so when it takes that broader view, it can see that the Bowen's disease or the Bowen's condition has infiltrated much farther rather than focusing just at that maybe the epidermis layer. Now it's looking more at the dermis as well and can see, okay, well the epidermis looks like Bowen's, but it's it's infiltrated into the dermis, and now we can consider that squamous cell. Another thing we were interested in trying is if we now do a few shot analysis to where we can, say you have a few annotated slides and you know where the cancer tissue is and you can classify, can we learn a generalized embedding of what that tile or tissue might look like? And so we take, I think, an annotated slide for each disease state, annotate. We have an expert pathologist at U Chicago who kind of helped annotate where certain tissues were, and then we can learn different embeddings for each type of tissue. So one of the things that was also interesting here, just one caveat, artifact is kind of when you think of an artifact in tissue, it's just like a water bubble or something that is just very spurious, and so we have to kind of account for that, or else the model doesn't know how to handle those. But when you start kind of in the bottom, right trajectory, that's kind of the epidermis. That's the top of the tissue, and as you kind of work counterclockwise, you hit basal cell carcinoma superficial, so the very top. If it's a basal cell at the very top of the epidermis, the nodular, which is a little bit lower. Then you've got Bowen's, which is also in the epidermis, but can then move to squamous cell carcinoma, which then kind of goes deeper into the dermis, which is the final. So you kind of see this transition of the top of the tissue to kind of deeper in the tissue through these embeddings. And when we apply these embeddings to a piece of tissue that the model hasn't seen, we can see it actually does a pretty decent job of identifying things like squamous cell carcinoma and Bowen's disease, as well as the dermis, which is kind of shown in the black, and the epidermis along the left side of the tissue. And so ultimately, what this more of a proof of concept, because there's a lot more challenges to deployability in healthcare. But it's a proof of concept to say, in these there's resource constrained populations that may not have access to experts, or maybe an expert is bottlenecked by the amount of data coming in. A deployable service like this, where it can either help make those diagnostic decisions or annotations to kind of show them where to look quicker, and kind of relieve these burdens and make increase accessibility to healthcare in these populations. So I want to finish with some of the current challenges in healthcare, or AI in healthcare, as well as kind of what the future looks like. So I broke the challenges. I like to think of them in 4 different ways. So there's the biological challenges when you think of machine learning in healthcare. So biological complexity. There's a lot of these multi-omics work at multi-scale, and so there's all these interactions that not a lot are fully understood. Diseases have a high level of heterogeneity, so the reason I may get a disease might be different than the reason you get it. General biological variability across populations. There's technical challenges, so data is fragmented across hospital institutions. It's very noisy. This creates things like distribution shift. There's been some work in federated learning to kind of address this, but it's been more of a proof of concept at this point. There's a lot of challenges with structuring or aligning how hospitals structure their data. There's high cost of false negatives. Like I said, if you want misdiagnosis, could be the loss of someone's life. Models have to be generalizable to handle distribution shifts. These can be distribution shifts across hospitals, how they structure their data. They can be shifts across populations. We've seen how underserved or more at-risk populations can have a very different health outlook. There's ethical challenges. So data is often biased towards specific populations. A lot of the data we've collected represents people who have access to healthcare. So there's that already implicit bias. A lot of it is focused on the Western and European worlds, and so a large portion of Asian and African and Middle Eastern populations are not fully represented at scale. So really, there's a lack of transparency for clinicians and patients. There's the ethical question of if AI does harm, who's responsible at that point, and then privacy and sensitive patient data. How do we maintain kind of security around that? And then lastly, operational. So, you can develop a great model that performs well, but it's important to keep in mind, how do we fit these models into clinical workflows? How do we, improve social acceptance of AI models? I think that's less of a challenge now with ChatGPT and Claude Code and everyone using these large language models. But 5 years ago, the thought of a computer controlling your health was probably scary to a lot of people. It's still scary to me. Models need continuous monitoring, and then very regulations. That could be a hospital regulation, and that's also the FDA regulations. But I want to kind of encourage us that as challenges increase, so do opportunities in this field. To tackle whether it's biological challenges, technical challenges, operational challenges. There's a lot going on and a lot of prospect here. So I'll finish with kind of the idea of what I think a lot of people in the field want to see for the future, and that's a closed loop learning system. And so I like to think of this, it's not specific to what it will be a digital twin, but it can be kind of shaped in the framework of a digital twin. So a digital twin, for those who might not be familiar, it's just a synthetic or digital replication of some sort of mechanical system. So we can think of a digital twin of the heart. And when you think of the heart, we can think of things like fluid dynamics. We can think of things of the electrical modeling, the actual physical tissue structures. And so we can deterministically model these using kind of the physics that we understand of the system. And so we can one of the first digital twins was actually kind of the cardiovascular system, where we can have this simulation of a heart system, and we can test different interventions on it, and it can also send feedback signals to say, hey, something's about to go wrong, and you can make an intervention in that way. The challenge is that a patient or a human is more than just the heart. So there's all these different systems going on. We've got neural systems, so the central nervous system, the brain. We've got cardiovascular systems, whether that's just the heart itself or all the veins and arteries. We got the metabolic system, the stomach, the intestines. We've got respiratory system, lungs. We've got the genes, protein interactions. So all these biological systems interacting together, and they're not all completely known. And so I think this is kind of where the field wants to move towards eventually. I don't know if it'll be in my lifetime, but this idea of a closed loop learning system where you can fully have this digitalized synthetic representation of what your body's doing, projecting your health outcomes, and then when it identifies something that might go wrong, for example, in that story where an AI system said we need to make a treatment for sepsis, calling for that intervention can kind of change those health trajectories for a positive outlook. So to kind of recast everything together all before we go, so healthcare is no longer just some domain that uses machine learning, but think of it as a large-scale, real-world machine learning system. It uses multimodal, noisy, and partially observed data. Particularly interested in predicting trajectories of patients, learning representations of patients, in order to estimate risk, as well as determine or optimize different policies for different populations. It faces many challenges ranging from biological complexity, data bias, missingness, fragmentation, and domain shifts. How we evaluate, oftentimes when there's unknown ground truth, safety and ethics, and then deployment into institutional systems. But we've seen this shift, from predictive models to decision-making systems, static models to continually learning systems, and population averages to personalized diagnostic systems. And so I like to tell people that when you think of machine learning in healthcare, the goal is not just to build a better model, but rather design a robust, deployable, and adaptive learning system that can be easily integrated into one of the most complex environments ever modeled, and that's the healthcare system, especially the U.S. healthcare system. And one of the things that the institute that I'll be joining, or I've joined, and I'm excited to kind of push the research through, is focusing on a dual perspective of keeping in mind both population and precision health, framing kind of our precision or individually tailored strategies with the mind of what sort of population they come from and the risks of that population. And so I will take any questions.
I'll take not the usual, so questions?
Like one complication I've heard about deploying like kind of AI for healthcare in the real world is often that you when you're using the system to like make a classification on a benchmark, when you then go to deploy it in the real world, you're now making decisions based on that classification, which kind of like changes the causal relationship between what like the AI system is doing and like what the healthcare outcomes are. And I've heard there are cases where like this means that the deployment doesn't go very successfully. So I'm curious, like what.
So I guess when you say like, so you make the prediction. I guess I had trouble following. So the model makes the prediction, and then you're saying.
Yeah, sorry. I wish I remember the details of this better, but I think something like if you, like, let's say that you're making a diagnosis for like some specific condition, and before the diagnosis would be based on like, or you're trying to like predict some like health outcomes of making some intervention, but before the intervention was being made based on factors that are not like the outcome of the machine learning model. But then like once you deploy the machine learning model, now like, that is being used in the decision making process, and that means that the results of making that intervention can change. So there's like this distribution shift.
So you're saying if for like I guess the machine learning is pulling away from like traditional. Are you saying you have the classical decision of like what a doctor would typically do without the model, and then the model changes that decision?
Yeah.
So I think that's going to just one of the challenges in general, especially that kind of goes to the false negatives, and a lot of times I'm trying to think of how to answer this the best way. So for me, like when I try to think of how to like approach that challenge, a lot of times I believe that when we have these models in the healthcare system and they make that decision, they need to also present why. And so for example, they present why, the physician can see that, have direct interpretability of why the model makes this decision, and now says, I agree or disagree. And ultimately, maybe if he agrees, that'll change the decision. If he disagrees and says the model, this is incorrect, it doesn't change it. So I think that is something, obviously that it can be an issue, but I think the interpretability approach kind of needs to be pushed to kind of address that. If that makes sense.
So you talked mostly about sort of the micro side. So it seems like AI on the macro side also sort of has maybe different kind of concerns. It may be less of the false negative issue, but more, in fact, maybe more of the issue that Kayleen brought up. So like at the macro level, there's a kind of causal network sort of thing. Like you said, income and education affect health. Probably not directly. It's not that now you have more education. So, but it's your income and education affect things like behavior, where you live, and those sort of things. And those things affect things that affect health.
Yes.
And so there's this kind of there may be question of where to intervene in this network, and once you intervene in that network, does that that could bring up some of these, like if someone has. Okay, let's give everyone, if you give someone $1,000, they have more money. Is that going to be like as if they organically had that extra money, or if you move them from one place to another, is it like the same thing as if they had organically done it? Maybe just there could be questions of how do you intervene? What's the most cost-effective or best way to intervene in this network to produce better outcomes? Feels like that's a question that's coming up. I don't know what you're.
Yeah, I mean, I guess that makes sense. So like, the reason I focus more on like the precision side is that's kind of what I'm more like research focused on, and my expertise are in. The population is still population approach is still new to me. But I can see the point. It's definitely a very interesting point. I don't know if I have a good answer for how to solve it.
I guess the one thing that seems interesting, like it's probably less of this false negative thing if you're talking about like a policy. It's like basically there's some policy in place right now. Maybe AI can look at data and propose some other policy to try. But of course, it's not seeing, it's kind of observationally proposing this policy, and maybe only if you actually try implementing it on some population, you see what the effects are. I don't know, I'm just guessing what kind of things might.
Yeah, I mean, population I think has its own set of challenges. The challenges I talked about were specifically designed for like the precision care, like in hospital. Like population health has its own form of challenges, which I don't really feel like an expert to fully covered.
Other questions?
Yeah, I'm just curious about the data that's available. Because I think, I don't know, I heard from somewhere that hospitals can't really share data because they're like legally not allowed to do so and stuff.
Yeah, so
So
there's
like how accessible is the data? Like,
so hospital data is very difficult. You generally have to get HIPAA training. If you're on a specific study, you have to get like IRB certification. And hospitals generally will not release data because just of the patient sensitivity. There has been work on federated learning to try to, they provide de-identified data to kind of federated models, and so there's really no sharing in that way. The other way that people are approaching it is for example, like the All of Us initiative, which a lot of hospitals are part of, but all the data is kind of going into one central, database repository in a kind of a standardized format for the cohort. Because when you look at across hospitals, one of the things is sharing is very difficult. Another thing is the way they do EHR and the way they organize their data is very different than another hospital. So when you try to bring both of them together, there's a lot of overhead work of trying to kind of align that. And the more institutions you bring in, the more that overhead becomes.
All right, thanks.